So I hope that by now I've managed to convince you that this picture depicting all four of the fundamental subspaces of a matrix is useful for problem solving and also for understanding. So what I'd like to do now is I'd like to further decorate that picture with more information so that we can solve and understand more problems. So let's start with the picture itself. Here we've drawn the generic picture of an m by n matrix, including all four of the fundamental subspaces. And what I want to start with is I want to choose one side of this picture and take a closer look at two vectors that might live on that side. So let's start with a vector v in the row space and a vector w in the null space. So those vectors live here. What I'm going to do now is I'm going to take an inner product of these two vectors. So let's look at the inner product of v, which again came from the row space, and w, which came from the null space. So I have my first equal sign here, and here what we're declaring is that v is equal to A transpose times some vector x. And this is exactly what it means for a vector to live in the row space. Any vector in the row space is some linear combination of the rows of the matrix, which means our vector v is equal to the transpose of A times some vector x. Great. So that's our first step here. Now we have another equals sign. Here we're moving A transpose over to the right-hand side of the inner product. And remember, we're always allowed to do this by the adjoint property of matrices and inner products. Matrices inside of an inner product can bounce back and forth, but every time we move a matrix from one side to the other, we have to transpose. So the inner product of A transpose times x with w is the same thing as x inner product with A times w, because we moved A transpose to the right-hand side of the inner product, and when we transposed the transpose, we got back to just A. Great, so that's our second step here. And now, let's remind ourselves where w came from. W came from the null space of this matrix. And that means that when we multiply A by w, we are guaranteed to produce the zero vector. So now we know that the inner product we started with, v inner product with w, by this sequence of logical arguments, is the same thing as x inner product with the zero vector. And of course, anything inner product with the zero vector is just equal to 0. So this argument is completely general. And what it says is that if you give me any vector in the row space and any vector in the null space, those two vectors are guaranteed to be orthogonal to one another. And the way we indicate this mathematically is we write null of A and then the orthogonal sign, col of A transpose, which is the row space. And what I like to do is I like to decorate the figure. So now I like to put a little perp sign or a little orthogonal sign between the row space and the null space to remind myself that everything in the row space is orthogonal to everything in the null space. Now, we could have done this argument by picking two vectors on the right-hand side here, so by choosing a vector in the column space and the left null space, and the argument would have been identical. So that's to say that the left null space is orthogonal to the column space. And we can decorate our picture on the right here with a little orthogonal sign. So here we have the general argument that tells us that not only do we have our four fundamental subspaces, but they're actually geometrically related to one another. Everything in the row space is orthogonal to everything in the null space, and everything in the column space is orthogonal to everything in the left null space. So we can state this as a theorem, and the way that I like to summarize this in my head is by saying that the fundamental subspaces of any matrix pair off into orthogonal complements. Everything in the row space is orthogonal to everything in the null space, and everything in the column space is orthogonal to everything in the left null space. We have notation that indicates this. So here it's appropriate to write the null space of A is the same thing as the row space, so the column space of A transpose, and then we put a superscript with the perpendicular sign. Same goes over here. it's appropriate to write column space of A transpose equals the null space of A raised to the perp sign. And then the same notation applies on the right over here. Oh, I guess we should say explicitly what this means. So for context here, so the reason this is useful is whenever we say that a vector is in the row space, what this means is that vector is orthogonal to everything in the null space. And when we say that a vector V is in the null space of a matrix, what this means is that vector is orthogonal to every vector in the row space. And the same language applies to the other side of our diagram. It's appropriate to say that the left null space, so the null space of A transpose, is equal to col of A raised to the perp sign. And it's also appropriate to say that the column space of a matrix is equal to the null space of A transpose raised to the perp sign. Again, what this means is when we say that a vector is in the column space, what this means is that vector is orthogonal to every vector W in the left null space. And when we say that the left null space is the column space of A raised to the perp sign, what this means is that saying V is in the left null space is the same thing as saying that V is orthogonal to every vector in the column space. So now we've added more structure into our diagram, and this more extra structure will allow us to think differently about many important problems.